We're going to look at iterative methods in this recording and the next couple, and the first method we'll start with is known as the Jacobi method. In order to illustrate how we'd solve the matrix equation AX equals B using the Jacobi method, we're going to consider a simple 4x4 problem. So we have four unknowns, x1, x2, x3 and x4, and because we have four unknowns we need four equations to uniquely specify these unknowns, and these are linear equations, and we're going to write them using coefficients a11, a12, etc. that we know, and a right hand side vector b1, b2, b3, b4 that we also know. So the unknowns here are the x1 through x4. We can write this set of equations in matrix form. Looks like that. So this is our matrix A, that's our vector of unknowns x, and that's our right hand side vector b. So the idea here is what we're trying to find a solution to this without inverting the matrix A. So this simple problem here, we can, if we wish, solve each of the equation for its unknown. So for the first equation, we say that the unknown is x1. What we can do, we take all of these things involving the other knowns and we can move them to the right hand side, and we can then divide by a11. The second equation, we say we're going to move this to the right hand side and this to the right hand side, and then divide by a22. So we end up with an equation x1 equals something, x2 equals something, and those equations look like this. That's just a simple manipulation of those equations at the top. Now, however, notice that our unknowns, the x's, appear on both the left-hand side and the right-hand side of the equation. So even if we went away and we solved this equation for x1, and then went down and solved the next one for x2, x3, x4, it would turn out that none of the equations would be satisfied, because every time we change one of these unknowns, we mess up all of the other equations. So in order to describe the Jacobi method, I need to introduce this idea of an iteration number. And I'm going to call the iteration number m, and I'm going to label the initial guess for xi as xi0. So in other words, xi0 is a number that somehow we've estimated from some method. Maybe we set it equal to 0, maybe it's come from something other else. Then we're going to go and use that set of equations that we just saw and calculate a new guess for each of the x's. Okay, the first new guess will be called xi1, the second guess will be xi2, then xi3, etc. And we do that for each of the different x's. So let's just have a look at doing this. So imagine that we have suitable values of xi0 for all of the xi. We're going to calculate a new estimate xi1 using the following set of equations. So let's just quickly have a look at this. For x1, the first iteration is going to equal the equation that we saw previously with all of the x's on the right hand side at our initial guess. So in other words, x20, x30 and x40. We'll then go to the unknown x2 and we'll say the first iteration is equal to this equation here. We're on the right hand side now. We're using our initial guesses for x1, x3 and x4. Then for x3, again we use the same equation using our initial guesses for x1, x2 and x4, and so on. Once we've done this, we'll have a new estimate for all of the different xi. It's our first estimate. Then, once we've done that, I'm guessing that we're unlikely to have satisfied the equation, so we need to go through and calculate our second estimate, and that's what the 2 here represents. It's not a power, it's an iteration superscript. Okay, so it's not x squared, it's the second iteration of xi. We go through, we do exactly the same thing. So the second estimate for x1, on the right hand side, we use the first iterate for x2, x3 and x4. The second guess for x2, on the right hand side, we use the first iteration for x1, x3 and x4, and so on. In general, once we've done this, m times the m plus 1th iteration is given by this. So we're just following the same pattern. x1, m plus 1th guess, depends on x2, x3 and x4 at the previous iteration. So we're updating these things step by step. So in general, if we have n equations, we can write that xim plus 1 is equal to this expression here. So the reason we split this into two sums is because xi appears on the left-hand side, it doesn't appear on the right-hand side. So we need to sum the product of the matrix coefficient and our unknowns at the old iteration. From j goes from 1 to I minus 1, and from j goes to I plus 1 to n, which is the last equation. So we can write this like that. So what are the sensible values for our initial guesses? That can be problematic. For some problems we know values at the boundaries, and we could use these, the boundary values, and then also xi0 is equal to 0 for any interior points. That's probably as good a thing as we can manage. For time-dependent problems, we could use the values at the previous time step. That actually makes a very good estimate in time-dependent problems. Otherwise, we need to make some kind of sensible guess. Often it doesn't matter a lot. Just as a slight aside, we can actually write the Jacobi method in more of a matrix form. So what we need to do is we need to split the matrix A into three components. A diagonal component, which contains just the diagonal components of A, a lower diagonal, where everything below that diagonal is push, and an upper diagonal, where all the points above that main diagonal are put. So A is equal to D plus L plus U, and if we go back to this equation here for the Jacobi iteration, it's actually pretty easy to show that we can write this in matrix vector form as our vector of unknowns is equal to D to the minus 1, so in other words this diagonal matrix here, that corresponds to that term there, multiplied by, and this is a vector multiplication, or matrix vector multiplication, B times the lower diagonal term, from j goes from 1 to I minus 1, minus this upper diagonal term. So that's just a simplified notation for writing this slightly messy location here, and you should probably demonstrate to yourself that this is the case. So the Jacobi method allows us to solve matrix problems without ever determining the inverse. So we're solving for the x's iteratively, without doing anything special. And usually it's determining the inverse of a matrix is the most costly part of a computation. In other words, it takes the longest time. So if we can avoid determining an inverse, that's a great benefit. So if we have a sufficiently large matrix problem, it's going to be faster to use the Jacobi method. But if the matrix gets big enough, or perhaps too big, the Jacobi method will not converge on an answer. It will iterate forever. So we're going to need to find improved methods.